Hello. In this video, we're going to be graphing trigonometric functions and identifying the shifts and period and anything else that we might need to help us graph these things. So in our first example, I'm looking at the tangent function. The official equation here is the tangent of theta minus pi over 2 plus 1. Now, because we're adding and subtracting that pi over 2 and the 1, means we're going to be shifting either left, right, well, both left, right, and up and down, okay? That minus pi over 2 being inside the parentheses means that we are going to be working left or right here. So inside the parentheses is typically opposite of what we would think. So it's a negative pi over 2, which means we'll actually be going to the pi over 2 units. The plus 1 on the outside indicates the up-down, and the outside is typical of what we would think. So the plus 1 at the back end just means we're going up 1 unit. Okay, so if I label my graph here, what we typically do, we'll call that 2 pi down here. This will be a negative 2 pi here, and we can fill in a little bit from there. There's pi, there's negative pi. What we typically do here, I will call actually this as 2, that's 4, here's negative 2 and negative 4. When we talk about the typical graph of tangent, we have at pi over 2 and negative pi over 2 vertical asymptotes. And then we graph with our rise, like a continuous rise as you read left to right. It's always increasing in this graph for tangent. The period of this function, because it repeats itself after this, and this length from asymptote to asymptote here is pi units, that means the period is pi. And it being a 1 theta there means that that has not changed, so our period will remain as just pi units. You can also see that the parent function typically starts at 0, 0, right here. But because we're shifting it to the right pi over 2 and up 1, it will actually start now at pi over 2 comma 1. And a period of pi means that those asymptotes are also shifting. So instead of being at negative pi over 2 and positive pi over 2, they've shifted to the right pi over 2 units. So there's one asymptote and there's the other. And you can still see how the period on this is pi units because the distance between the asymptotes is 1 pi. All right, and then from there, from that point, we'll just do our typical drawing for tangent. And as it is with any other trig ratio, from here, this is just infinitely repeatable as you go left and right. So from pi to 2 pi, we should have another one. So we'll have more asymptotes at 2 pi. And we'll start at 3 pi over 2 comma 1 and do our drawing. I can also go to the left, start at negative pi over 2 comma 1 and do our drawing. And then again, at negative 2 pi, we'll have a vertical asymptote starting at negative 3 pi over 2 comma 1 and then do our drawing here. Okay, so that's what this tangent function looks like. The dotted pieces, the asymptotes, are not actually on the graph. The only pieces that are on the graph are the always increasing chunks as you read left to right here. Okay, let's look at another one. In this example, we're looking at secant's function. Secant is a reciprocal of cosine. So we're going to end up having to graph the cosine function and then using that as a guide to help secant. So let's talk about the period first. Typically, the period on cosine is 2 pi. But we do have to adjust it because we do, in this case, have something multiplied by theta. When we have something multiplied by theta, like we have here inside the parentheses, that's going to affect our left and right growth. So we're either stretching this or compressing this graph left and right. based on what's multiplied by theta. Well, what's multiplied by theta is 1/2. So I end up dividing 2 pi by 1/2, and we find that our period is 4 pi. Shifts, we have nothing adding or subtracting on this function, so we actually have no shifts on this whatsoever. But that 3 out front makes us want to talk about our amplitude being 3. Now, secant doesn't actually have an amplitude because it grows forever. So this does not apply to secant, but what it does do, it applies to cosine. And that, again, cosine is what we're going to end up graphing first just to get a view of what this looks like. All right, let's set up the graph the same way as what we did before. So we'll put 2 pi there, negative 2 pi here. I'll go as low as negative 4 and up to 4 on the y-axis. And we can just fill in a little bit here just to kind of make this more notable what's going on here. Now, cosine. Cosine typically starts at 0, 1. However, because the amplitude sitting on cosine right now is 3, it's actually going to start, because of its vertical stretch, at 0, 3. From here, it normally does a down and back up over the course of 2 pi. However, in this case, because the period is 4 pi, and 4 pi is the full length of this graph here, it's not actually going to be able to pull that off. On the right side, it will first hit 0 at pi, and then will finally hit its lower valley at negative 3. Okay, and so that's what it looks like on this side here. On the other side, it's kind of doing a flip of this. It'll hit 0 at negative pi, and then finally get to negative 3 at negative 2 pi. And that's what this side looks like. Now, the whole purpose of graphing cosine, again, was as a guide. And we know whenever cosine hits 0, its reciprocal, which is secant, will be undefined, because 0 flipped becomes 1 over 0 and is undefined. So we have two situations where we're 0, once at pi and once at negative pi. Now, anywhere this function, this cosine graph peaks, we have a basic, what looks like a parabola. It's not exactly a parabola, but it's a growth up, and any valley has a growth down. And this would go the other way as well. We just can't see where the other asymptote is. Same over here. It's going to come down this way, and it will go the other way as well. Again, we just can't see where that asymptote is, and so it'll end up roughly looking like that. And again, this is infinitely repeatable as you go left and right on this. Okay, so that's graphing a couple trig functions there. For now, we are done.